Okay, so 4.2 is called the natural exponential function. Okay, so the natural exponential function is what? Do you guys know what it is? E. Okay, so we are going to graph exponential functions with base E. So that's what we're going to do first. We are going to solve real-world problems with exponential models, including models with continuously compounded interest. Hey, remember that your quiz is tomorrow over 4.2. We are going to be using our graphing calculator today, and you are going to be able to use that on your quiz tomorrow, but you will not be able to use it on your Chapter 4 test, which is why I told you that you need to have your scientific one. Okay, so starting on Monday, we'll exclusively be using our scientific calculators. Today we are going to need it as we investigate some real world models. And then as we're going over our notes today, I'll kind of talk to you about things that we will see on our quiz. Okay, so the first thing we're going to do today is talk about the graphing aspect. So the natural exponential function is something that you've graphed before. We even talked about yesterday the transformations that go with it. And here they just give you the equation. We're actually going to draw a little graph that goes with it. Okay, so the natural exponential function is f of x equals e to the x. Again, you should be familiar with this from previous classes. Okay, and then your base is going to be e. So it is often referred to as the exponential function. Let's go ahead and just draw a sketch of the graph of the parent function. So like y equals e to the x. Based on what we did yesterday, can you guys predict where the asymptote's going to be? Y equals 0, because there's nothing added to the end, so it is going to be at y equals 0. Okay, and then do you guys know what E is approximately? Yeah, 2.71, which is going to help us with one of our points. What is the y-intercept? 1, because if you plug in 0, e to the 0 power is 1. Okay, so the y-intercept is 0, 1. Okay, and then that means at 1, I would be at e to the first, which is approximately 2.72 if you round it. Okay, and then we are going to go ahead and curve that up. And then just like yesterday, the domain is still going to be all real numbers. And then our range for this, if we look at all the points, they're above 0, so 0 to infinity. Okay, so very similar to the growth that we were talking about yesterday. For our first example, we're going to sketch the graph of the function, state the domain, the range, and the asymptote. We are, again, scientific calculators are what we want to practice this on. For your quiz, you're not going to have to graph the points of the function. That's something that you will do on your Chapter 4 test, which will be scientific calculator only. You will have to identify parts of the graph, though. So like the domain, the range, the horizontal asymptote. Okay, I'm just letting you know that, so when you practice without using the convenience of having the graph there for you. So thinking about what we did yesterday, we like to start our table in the middle. And what would be the middle of this? What would be a good value to put in the middle of our table? 0. This is very similar to the parent function. What is the only transformation happening here? Yeah, so if you have the negative, that means it's a what? Reflection over, not the y, the x, over the x-axis. Well, and we'll be able to see that in a second. If it's on the outside, it's over the x. If it's on the inside, which the inside would be the exponent, it's over the y. Okay, so let's plug in 0. If I plug in 0, e to the 0 is 1. So this would just be negative 1. Okay, and then you guys will have to find how your scientific calculator works. Were some of you able to find those at home? Steal them from your middle school siblings, maybe? Find them from your own middle school days? So like mine, my e is going to be in this log function. Do you guys know why e is in the log functions? It's, yeah, what's the relationship? Wait, say it again? Yeah, okay, so yes, to undo a base of e, you use the natural log, which brings down the exponent, and that's because what type of functions undo each other? Nope. Multiplying a fraction by the reciprocal undoes it. What are they called when they undo each other? Yeah, inverses. Yep. Okay, so if I did negative 2, okay, then I would get negative, and we'll just round to the nearest hundredth, 0.14. And then my scientific calculator is cool because I can just arrow up and then change this. But then I have my negative 1, and then I can just go up and change this to 1, then my little delete. And then think about if this is what you anticipated. So this is just the opposite of e. Okay, so e, let's actually write down that approximation. We'll write it down up here. So e, or e to the first, is approximately 2.71828. E is very similar to what other mathematical symbol? Pi, because they are both what? Irrational, which means that they continue forever. All right, so then let's go ahead and graph it, and then we'll do our domain, our range, and our horizontal asymptote. Okay, so at 2, I'm at negative 7. So if I'm at negative 7, what's a good scale to go by? 2's, right? So then here I'd be at negative 10. Here I'd be at 10. But I can still make my x's go by 1's. All right, so at 1, 2, I'm at 2, 4, 6. And then 7.39, so I'm going to estimate about right here. At 1, I'm at negative 2.72, so 2, and then here would be 3, so a little bit below 3. At 0, I am at negative 1, which would be halfway. And then I can see that these values continue to do what? Good. They're going to get closer to 0, which is our x-axis, which means, Kelly, what's going to be our horizontal asymptote? Good. Okay, and then don't forget your y equals, like she said, y equals 0. Your domain, similar, all real numbers. Okay, when you're picking out what your range is going to be, remember that your range starts at the lowest point. I'm going to put in my horizontal asymptote as well. Okay, so think about your lowest value of the graph. Anna, what's the lowest value that this graph is going to reach? Negative infinity. Good. Okay, so that means that's where I want to start my range, is at negative infinity. And then, Reese, what's going to be the second part of my range? So what's my highest value? Yep, and it won't ever reach 0, but that's what it approaches, so we're going to use 0 with our soft bracket. All right, let's look at g of x. So for b, we're doing g of x equals negative e to the power of x minus 1 minus 2. Okay, and then again, we talked about how that was a reflection over the x-axis. For b, this is also a reflection over the x-axis. But then we have a couple of other transformations, right? We talked about this yesterday. What does this minus 2 mean? You're going down 2, and the minus 1? To the right. Because remember, when it's in the exponent, it's the opposite of what you see. Okay, so 1 unit to the right and 2 units down. It's really going to be this function, except all the points are going to be moved. 1 unit to the right, 2 units down. Okay, so we can actually do that on our table. Now, when you're starting your table and you want to be in the middle, if you moved it 1 to the right, where should my middle x value be? It should be 1 to the right of 0, which is? You can also think of it as if you plugged in 1, that would give you 0. And then we just like to go 2 up, 2 down. All right, and then, like I said, you can either plug them in, or you can think of it, oh, if I'm going 2 down, 1 to the right, we already took care of the 1 to the right, now we're going to do 2 down. We can check it for when we plug in 1. When I plug in 1, 1 minus 1 is 0. Anything to the 0 is 1. So this would be negative 1 minus 2, which is negative 3. If I plug in 2, can you guys see that this is going to be negative e to the first minus 2? Okay, so negative e to the first was this. So if I subtract 2 from that, I should get negative 4.72. For the next one, I move that 1 to the right. 2 to 3 is plus 1. So to get the next one, all I have to do is take this and subtract 2. Can I verify that on my calculator? Yeah. Okay, same thing for these. If I just subtract 2, negative 2.14. If I subtract 2, negative 2.37. Okay, now it looks like these numbers are getting closer and closer to what? Negative 2. Your domain is negative infinity to infinity. We talked about yesterday how if you have that subtraction on the outside, that is going to be your horizontal asymptote. If you didn't put in your horizontal asymptote, will you go ahead and do that? I actually like to put it in first if I know what it is. That way I know what it's approaching. So, oh, and this I am going to go by 2's again. Again, if you look at your scale, right, this would be negative 10, 10. Here I'm going to go by 1's. So then if I'm going by 2's, this would be at negative 2. So that's my horizontal asymptote, and now I can plot my points. So at negative 1, I'm at negative 2.14, which is really close. At 0, negative 2.37, where this is 3, so I'm about here. At negative 1, I'm at negative 3, which is halfway. Negative 2, I'm at to 4.72, which is close to the 5 mark. And at 3, I'm close to 9.5, which I would say is about here. And then when you connect these, you're going to be connecting them with a curve. Okay, and they are getting closer and closer to that value. All right, and then Corbin, what's my range going to be for this?
Negative infinity to -2.
Good, okay, and again, your lowest point goes first. Oh, I wanted to write that for the last one, just as a reminder for you. Okay, so you always start with your lowest point, and then it's going to go to your highest point. If you're having trouble with the range, that's a great way to think of it. Oh, this is continuing on forever. It's going to go to negative infinity, and then it's going to go up to -2, very close to it. So we have our soft bracket. All right. Now we're going to start with some story problems. Yes. Okay, this is going to be an exponential growth model. So it's going to model a real situation. And we have an infectious disease. It is spreading in a small city that has a population of 8,000 people. After T days, the number of persons who have succumbed to the virus is modeled by the following function. Okay, so we do need to understand what our variables represent. So your T is going to be your days. Okay, what does the V of T represent?
The number of people.
Yeah, the number of people who have the virus. So what we want to do is figure out how many people were infected initially. So how can I do that? But yeah, I can plug in 0 for T, right? How many people at time 0 are infected? This I can actually do without my calculator. So if I'm finding V of 0, I have 8,000 divided by 4 plus 1596, and then it's e to the negative 0.95 times 0, which is really just e to the 0, right? What's e to the 0? 1. So 1 times this is 1596. 1596 plus 4 is 1600. And if I'm dividing by 8,000, right, I can divide both of these by 100. What's 80 divided by 16? 5. So 5 people. Okay, so initially there were 5 people that were infected. Now what we're going to do is figure out how many infected people there are after 1 day, 2 days, 6 days. And I'm going to show you how to do this quickly with your graphing calculator, instead of plugging it in over and over and over again. Do you guys know how you can use your graphing calculator to help you? Yeah, you plug in the equation, right? So if you go to your y equals, I'm going to plug in 8,000 divided by, and then the rest does have to be in parentheses because I have more than one term. So 4 plus 1596, my e is here above the natural log, negative 0.95x, and then close my parenthesis. And then I can just go to my table. Okay, so if I want to start at 0, this is a good way to check. Make sure at 0 you're at 5. You already found that. When you are doing this, when you're determining the number of infected people, you are going to use your normal rounding rules. Now when I say that, it means if you have 0.5, you'd round up, 0.4 below, keep it the same. Okay, so when I look at V of 1, I have 12.877, which is going to be approximately how many people? 13. Okay, then I'm going to go to 2, which is 32.96, so that would be approximately 33 people. And then for 6, it would be approximately 857 people, which that escalated a lot in those 4 years, right? Right? And sometimes you are going to round like down, like see how that one was 0.23, so it'd be 449. It just so happened that all these were 0.5 and above. Okay, so for the next one, it says roughly how many people eventually get infected. And then I gave you a hint. So, bless you. First, let's think about what type of function this is. So, based on these numbers, you can see that they're getting bigger. So, we would assume it's what type of function? Exponential growth. So, well, and it is exponential growth. So, if you have a regular exponential growth, and what I mean by that is something like y equals a to the x, the right side of the graph is going where? To infinity. All right, now if we think of this in terms of real world problems, if this goes up to infinity, that means that the whole world is going to get infected with that disease. Does that seem accurate? Some of you aren't saying anything. No, right? Did everybody die of measles or polio? Not yet. Okay, so let's think about what are some natural causes that are going to not make this reach infinity. What are some likely things that happen?
Everyone infected dies.
Okay, if all the infected people die, right? Then the disease dies with them. What else?
If we quarantine
The ocean
If they-
blocks the continents.
But then still, it's still not probable that everybody on the continent would do it.
Fish that can't be infected by humans.
Medication, right? So doctors are going to find medication, vaccines, help find a cure for it. Right? That's another good thing. Why are you laughing? Those are both great reasons. Okay? So based on that, based on what we were talking about, it's not going to go to infinity. Eventually, what's going to happen is this is going to level off. Okay, so it's going to reach a maximum value of the number of people it infects, and then hopefully it'll stop. To find this, you can look at your graph, and I want you to just graph it. Oh, no. I want you to just graph it on your standard window right now, which most of you guys already have it on your standard window, right? Okay, so on your standard window, it does look like just a normal exponential function. If we extend our window to some bigger numbers, like maybe our x, we'll take that out to 100, you can go by tens, my y, I'll take up to 3,000. You have to like play around with what it is. I'll go by hundreds. Okay, and even you can see like my x's, they started right away, so I could pick a smaller value for my x's. But you can see that you have this line, okay, that looks like it's constant or is approaching a constant. You can look at your trace. You can also look at your table for very large values. So if you want to start at 50, also go by fives, see what happens, right? Can you see how these are all your same value? So eventually, how many people are infected? 2,000 with this model. All right, so it's going to be about 2,000 people. Okay, and you can look at the graph or the table, and then I'm just gonna draw this on there for you, for your model, right? So you're looking to see what value it converges to. All right, let's try another one about skydiving. My worst nightmare. A skydiver jumps from a reasonable height, above the ground. The air resistance she experiences is proportional to her velocity, and the constant of proportionality is 0.2. It can be shown that the downward velocity of the skydiver at time t is given by the following equation. Now, they tell you that t is measured in seconds. Your v of t, which is your velocity, is measured in feet per second. And then they give you your equation. So you have all these values in here that you don't necessarily have to compute anything with. If you look at the constant of proportionality, does that show up in our equation? Yeah, it's in front of your t value here. All right, so this is going to be the equation that we're going to use to help us find the initial velocity. Again, this is something you can do without your calculator. You can just plug in 0. So we have 80 times 1 minus e to the 0 power, which e to the 0 power is 1. 1 minus 1 is 0. So 80 times 0 is 0. Okay, so does this make sense? If no time has passed, that the velocity is 0 feet per second. Yes. Okay, because technically she hasn't jumped yet, so she doesn't have her velocity. Now we're going to find the velocity after 5 seconds and 10 seconds. So just like we did before, we can use our graphing calculator to input the equation, and then that just helps us find those two values quickly without having to plug in the values twice. Okay, so you have 1 minus e, negative 0.2x. Okay, so you're going to have that in your y equals. And then if it's 5 and 10, if you want, you can start at 0. Make your table set go by 5. Okay, so at 5, and then we're going to round to the nearest tenth for this. Really, if it doesn't say what to round to, you can pick whatever you want. Okay, so after 5 seconds, her velocity is 50.6 feet per second. Would you predict the next one to be higher or lower? I know you can see it's higher, but why does it make sense that as time continues, her velocity is higher?
Isn't there like a terminal velocity?
Yeah, there is a terminal velocity. Are some of you guys doing physics this year too? And you guys talk about like your velocity? What's that? In physics? Right, so it makes sense that she's gaining momentum after the time is passing and her velocity is increasing. All right, and then we're going to draw a graph of the velocity function, and then I want you to make sure that you're labeling your axes. And we do want a good picture of what is going on. You can look at your table here. Remember, I went by 5s. That this looks like it's getting closer and closer to what value? 80. So maybe I want to keep going and see when it does reach 80, 60. So my graph that I'm making, I might want to put that out to 60. And then my y-axis, I want to go up to what? Yeah. Okay, so then this is my time in seconds. And then I can go by 5. So 5, 10, 15, 20. Oh, if you went by 10s, that's fine. You didn't go by 1s, right? Oh. Okay, Okay, and then I know I only have to deal with the positive here because my time is going to be positive. My velocity is going to be positive. And then here I'll just go by 10. So 10, 20, 30, 40, 50, 60, 70, 80. And then I'm going to go ahead and label this. So this was my time in seconds. This is my V of t, which V of t represents what?
Velocity.
Good. And the velocity is measured in feet per second. Doesn't it look so beautiful? Okay, and then so now I can plot some points. Now I already have some, right? From part A, it's 0, 0. From part B, I have 5 and then 50.6, which is really, really close to 50. Here I have 10, which is close to 70 there. And then I can just go ahead and pick some. Remember, I went by 5s here. Okay, so at 20, I'm at 78.5, which is close to 80. Really, as you keep going up, what's going to be happening? It's going to increase until it gets to 80. So is terminal velocity something you guys discuss in physics? Say no. Okay, so our last part, part D, does talk about the terminal velocity. So the maximum velocity of a falling object, with wind resistance, is called its terminal velocity. Okay, so from our graph in part C, we are going to find the terminal velocity of the skydiver. And then it says to explain. So we're going to practice on writing a complete sentence, thorough explanation. Okay, so your max velocity, we already talked about what it was. What is your terminal velocity? And what was our value? What did we say that these numbers were going to?
80.
Yeah, and look, if you go to 50, you can see all of these are 80. Okay, so your terminal velocity is going to be the 80 feet per second. All right, well, how did I find it? To find the terminal velocity, what did I use? I used my table, right? So to find the terminal velocity, I used, I'm going to say my table and graph. And what value was I looking at? Your y values, right? I was looking to see what happened with my y value. How did I know it was 80? Okay, so it leveled off at 80, right? It stopped increasing, plateaued. Have you guys talked about the word like converges? If it converges to a specific value? We will talk about that word more in the second semester. But converge is a proper term when it goes to a certain value. So I use my table and graph to see which y value the graph converges to. Which is 80. We examine, so in order to get to 80, what did I do with my table? Because if I just left it as going by ones, right? If I just left it as going by ones, would I get there? No, so I had to look at values of x that were what? Bigger, large values of x. I have to see what happens as x is going towards infinity. Okay, so we can say that we examine large x values to determine this.
Are we gonna have more explanation questions on the quiz with less guess?
That I can't. Yes, yes, you'll for sure at least have one, but we'll do some more practice with that today as well. And we'll continue to do that too throughout the year. All right, so the second part that we're dealing with is all going to be about compounded interest and this type that is continuously compounded interest. So this is the formula that you guys probably already have memorized. You guys remember your PERT formula? Your PERT plus formula? Shampoo of Champions? Do you guys even know what PERT plus is?
No.
I used it as a kid. Had a beautiful mint green bottle. PERT is your continuously compounded interest formula. Remember the formula that we talked about yesterday was just for compound interest, and there were different ways you could compound it. This is when it's continuously compounded, which means the interest is compounded at every instant. So yesterday we saw that the interest that's being paid So we saw yesterday that the interest amount paid increases as the number of compounding periods increases, which means if you had the choice, would you rather have it compounded quarterly or monthly? Monthly, because why? More compounding, right? There's 12 months in a year versus 4 quarters. Which means if you have the same conditions, the same principal, the same rate, what would be the best? Yeah, every instant, which would be continuously, okay? So if you have the same conditions, this would be the best. If your conditions are different, you're going to have to do some tests, which we'll do later. You can see that your values are still the same, so A of t is the amount, P is your principal, interest rate as a decimal, and then the number of years. You will have the two equations at the top of your quiz tomorrow, but they just won't be labeled, so you'll have to know when you're going to use it. For our first example, we have $2,000 that is put into an IRA that earns 7% a year. So 2,000, 7%. Just like we did yesterday, I like to just label, this is my principal, this means my rate is 0.07. And then I have to find the amount in the account after 10 years if the interest is compounded continuously. Okay, so when it says find the amount, I know I'm finding my A of t. After 10 years means that my time is 10. This is compounded continuously, which means I have to use my PERT equation. All right, so then my A of t, or my A of 10, because that's my years, is going to be my principal, 2,000. 1 plus, my rate is 0.0, oh, sorry, what am I doing wrong? Yeah, that's your regular interest, right? So I have to do P, and then it would be times E. So my A of 10 is going to be 2,000 E to the power of 0.07 times 10. And I'm writing the multiplication like that because if you're putting that into your calculator, do not close the first parenthesis. Really, I would do this part in my head. What's 0.07 times 10? Just 0.7. You just move the decimal place over, right? Okay, so 2,000 B, and then this would be, oh, this one, if you have a calculator like this, you won't even put those in, but when you're dealing with money, you always round to the hundredth. You're always going to round to your nearest cent. Okay, so for these, it's really just practicing on your calculator, making sure you're entering it in okay. Your setup is usually the simple part. That's where people mess up. Now for B, you're going to find the amount if it is compounded hourly, which means we are not using our continuous formula. Oh, sorry. This means you're using your A of t equals P 1 plus R over N to the NT power. Now, whatever you used in part A here, this is going to stay the same. So your principal is still 2,000, your rate is still 0.07, and we're still going to use the 10 years to compare it. Okay, so your T is 10, your P is 2,000, your rate is 0.07. Now, in order to find all these, if it's compounded hourly, okay, to find the value of N, what is the question I have to answer? Yeah. How many hours are in 1 year? All right, how can I find that?
20 hours.
Days of the year.
So, yes, well, and start with something that you know the hours in. You know how many hours are in a day, right? So 24 hours in a day, and then how many days are in a year?
365.
Days in a year. Do you guys remember these from chemistry?
Yes.
Okay, like the day and the day cancel out, so then we multiply them together, and how many hours are in a year?
8,760.
8,760 hours per year. So then that is going to be your value of N. So your A of t or your A of 10 is 2,000. 1 plus 0.07 over 8760. And this is 8760 times 10, which is really just going to be what?
7,060.
All right, and then again, we'll round to the nearest cent, and you should get 4,027. And do you expect these to be, do you expect this to be smaller or larger?
Smaller, but not that much.
Yeah, it is going to be smaller, right? We expect that. But yeah, it's only smaller by a small margin. Okay, so it is only a small margin. However, when it asks you which one is going to give you the better return on your investment, technically it's what? It's what we did in part A, but what did we do in part A? Continuously. So let's write this out. Compounding continuously. This is the type of explanation you'll have to write on your quiz. So compounding continuously will earn you 2 cents more, giving you the better return on your investment. Okay, so this is nice. I can tell just by reading the sentence the question that you answered and why it's better. Okay, so compounding continuously, that's what you want to use. It'll earn you 2 cents more. That gives you the better return on your investment. All right, now, for example 2, it says which of the given interest rate and compounding periods would provide the best investment. So best investment means what? Which one's going to give you the most money? And then I have to explain my findings. So in the first one, they give you 3.5% per year. It's compounded quarterly. So the 3.5% is giving you your rate. 3.5% would be written as 0.0, good, 0.035. Okay, you can think of it as 3.5. You move the decimal over. If it's compounded quarterly, your end value is 4 quarters in a year. Okay, so 3 1/4 is 3.25. So as a decimal, it would be 0.0325 compounded monthly. 12 months in a year, compounding continuously. All we need for this is the rate, because we're going to use E. All right, now if I'm going to use my equations, what else do I need? Okay, so I need to know the time and, yeah, whatever your initial investment is, right? Okay, so for these two, I'm going to be using this formula. Okay, for this one, I'm going to be using A of t equals PE to the RT. If you're comparing these, doesn't matter what your initial value is, as long as it is the same when you're comparing. Same thing for time. So you can pick whatever investment value you want and whatever period of time that you want. Okay, as long as you keep it consistent for all of them, you're going to get the same result. Obviously, depending on what you invest and your time, the differences between them is going to fluctuate. Okay, but we can use $100 if we want. What would be an easy year to compute? 1. 10 would be fine too. You do have to use at least 1. Okay, so your principal we said was 100. Our time we said was 1. Again, when you're doing this on your homework, you can choose whatever value you want. It'll only affect your explanation at the end. Okay, so I'm going to give you some time right now to do your A, your B, your C. And I'm going to use the rates as because I'm here. All right, and Nora, can you tell me what you got for part A?
103 and 55 cents.
Thank you. Do you guys agree with that? Of the 55 cents? Okay, and then Reese, what did you get for part B? Oh, really? You can tell me what C is. What's C? Good. Hannah, did you do B?
Yeah, I got 103, and 30 cents.
Good. Okay, now even before we did this, right, we couldn't just say that compounded continuously was automatically going to provide the best return. We can see it doesn't, but why?
That's different.
Yeah, you have different rates. See how your values are not the same for all of them? Your interest rate is the lowest for this one, okay, the highest for this one. So based on our results here, what is going to be the best return on our investment? A. Okay, and then we're just going to explain why. Okay, and choice A is the 3.5% per year, compounded quarterly. Okay, so I could say choice A, 3.5% per year, compounded quarterly. Would be the best investment. Well, why is it the best investment?
More money.
Yeah, okay, so it would be the best investment because it gives you the best return on your investment. Okay, you could also add on how much difference it is. There are some questions that ask you to specify that, how much it is. So you could say choice A, earns you, so how much more than choice B? 25 cents more than choice B, and 50 cents more than choice C over a 1-year period with $100 invested. Okay, so we only invested $100 and that's only 1 year. So if you made your principal amount more and if you increase the years, you're gonna see a much wider gap between these. So now it's changed, but if, like I said, you made this 1,000, 10,000, made it over 10 years, you're gonna see more than just change. Okay, so over time, you're gonna see and reap those benefits. All right, I'm gonna give you your homework from your calendar.